Hello everyone, Ashley here, and I've decided to do this tutorial because I received one email from a student from your classmate asking me to explain three things. So the first thing I have to explain is the systematic. No, sorry, not this one. The random component. The second thing that I was asked to explain is the residual, right? That's the second thing. And the third one I have to explain is data transformation. So these are the three things that I will focus on before I move on. I hope you've been listening to the lecture captures on UniHub and that you understand what we've been discussing on the chapter correlation and regression and on multi-regression. Please also make sure that you practice your lab work on SPSS. Whatever I'm going to do today will be just not to waste time, will be on Excel, but you know how to work on SPSS. Instructions have been given to you, so the output might be different, but the results are the same. Now, let me start with page 12, right? So, a linear model, remember, there is a difference between a straight line and a linear regression model. So a straight line will be here, y equal to mx plus c, y equal to a plus bx, y equal to alpha plus beta x, full stop. That's what a straight line is. But the model, the formulation, the equation, the formula of a linear regression, of a simple linear regression, takes into consideration something here, the epsilon. You might think of it as errors, but I think we should discuss the errors later. I think right now let's approach this from a different angle. So what it means here, so I think this is the first question, explain the meaning of random component. So it represents an explained random variation. I'm just reading here and I will explain in a minute. And the random component here identifies the response variable y-axis, right? The y, and gives the distribution of the y-axis. I don't want to go into details about what type of distribution, but right now we can assume it's a normal distribution. But trust me, it can also be binomial distribution. We can come back to this later. So what it means here is uh, the straight line that we got here. Forget about all this right now. The straight line that we got here is obtained because of these crosses. These are the true values, true coordinates. Now, the moment I move one x value, the y value will also respond and we'll get a new y value. So with these changes in x, I can have new y values, and this is what we are talking about. This is what the uh, random component of the model means. So uh, you can imagine the millions and millions of straight line I could have put in here. One slight mistake I make in the x reading, I would have got a distorted coordinate, and then I would have not received the perfect line. I would have got another line. So this is the type of errors I'm talking about here. Now the response here is what has been identified as the random component, and it follows, like I've said, in normal distribution. So I hope this is understood, but I think it will be better if let me see what I have. Yeah, um, right now I will just ask you to try and connect this with page, I think 16. Yeah, 16. So it is different to this one. Sometimes student uh, kind of confuse these two, residual analysis and the random component. So I hope it makes sense. Before I speak about residual analysis, let me quickly summarize random component. It is what identify the response variable y. So and it gives the distribution of the y response axis. What it means here is the straight line that I get, the y values that I get from the straight line is fine. I can substitute my x value 1, 2, 3, 4, 5 in the equation of the straight line, and I can get a y. But this can vary. The y value, the straight line itself can change if I decide to give you another coordinate. Remember, the straight line is obtained by having the best fitted line. So if I had given you another coordinate, the original straight line would have been different. It would have been something different. Let me try to put that in context. Let's say I am yeah, let's take this example. This is the example with years of experience and the annual sale by student, right? Now, how do I get this data? I've chosen one person, one arbitrary person who had 1 year of experience, and that's the annual sale. Let's say that person's name is Ashley. But what if instead of taking Ashley, I had taken John, who also had a 1 year of experience, right? So instead of Ashley, who has 1 year of experience, and who made 40,000 pounds in sales, what if I had chosen another person called John, who also has 1 year of experience, but who had a different annual sales? So that would have been different, and I would have got a different coordinate here, and hence I would have got a different straight line. So that's what the random component of y means. I hope it's clear. The second one that I want to talk about, that I have been asked to talk about, is residual analysis. Now that's the error. Let me focus here. Again, remember, you're supposed to do that in Excel. In SPSS, I have done that in Excel. That should not be such a big problem. What do I have here? Right. Okay. So I've taken the example on annual sale and years of experience. This is the true value, and I can have the estimated value, and I can find those values by substituting x here. So I can say 2.6242 multiplied by the x value plus 39.867, right? So that's the estimated value of someone who has 1 year of experience. That's the true value, that's the estimated value. Now clearly there's an error. Can you see? This is the true value, and where it hits the line, so that's x equal to 1 around here. Maybe I should talk about this one then. Let me talk about x equal to 2 because you can see it. Right? X equal to 2 is here. The true value 49 is the dot, and 45.1154 is where it would hit this line, and it would give me a reading of about 45.1154. So the difference between the true value of 49, which is around here, and 45.1154, which is the estimate value, that's called a residual. That's called an error. It means there is a discrepancy between what I thought would happen and what actually happened. What I thought would happen and what actually happened. So there's an error, a discrepancy. And to find that, it's the true value minus the estimated value. There you go. Right, so the minus here would tell me that there has been an overestimated. I overestimated by this amount. So if the sale true value is 40, then I forecasted 42.49127, whatever. Right. So this is the error that we call here. So how did I? Don't let this scare you. I think that's why I got this question. Error is equal to the true value minus the value that I got from the straight line. That's exactly what we did. Error is equal to the true value minus the value that I got from the straight line. There you go. Error is equal to the true value. Error is equal to the true value here B2 minus the value that I got from the straight line C2, which, see how I got it here. Oops, daisy. So C2. This is how I got the straight line. So that's what residual error is. Right. So I'll let you read the rest, and I think we can find we have plenty of lines that we can dump, we can fit into across those points, and the one which gives, we can square those errors, we can find those the sum, and the one which gives me the least one, the least numerical value out of thousands and millions of lines, that would be the line of best fit. That's how we proceed to get the best fitted line. Okay, the error usually follows a normal distribution. Let me see if I can discuss anything here. Right, maybe up. I think we discussed this. I don't know if I have it. Anyway, the error should be, yeah, I can discuss that later. That's fine. The errors, if I have to plot this error, these data, right there you go. I can plot them. Errors should be scattered all over the place. There should not be any specific pattern. It means that if there is no pattern, it means that I cannot focus errors. If I can't focus errors, uh, it you know, if I can't focus the errors, it means I can't really focus an exact value of y. Otherwise, I would know an exact value as a forecast. So that's why we want the errors to be perfectly scattered all over the place. There should not be any specific pattern yet scattered all over the place. Right. One thing I forgot to discuss here, just came across my mind, is page 12. I saw that. Right. Uh, right here. How do we discuss gradient in the world of management and in the world of business? Right. So this is what I'm trying to explain here. The gradient, and I'll focus on the value here, beta, which is the gradient. Now quickly, what you should know by now is another word for gradient is slope, and gradient is usually found or calculated by using change in y divided by change in x. This is what you've seen before. This is how you calculate gradient. Now this is just notation wise. Change is denoted by a little triangle here, change in y divided by change in x. Now for you management student or business student or finance student, when you are asked to explain the meaning of gradient, so for example here, what would be the meaning of the gradient, which is 2.6242 here, what would be the meaning here? So we don't just say, oh, this is the gradient or this is the slope. We explain it, and to explain it there is a little bit of mathematics. I don't think it's too tough. Now I'm going to just play with this formula here. To explain gradient, I'll look at a specific denominator. Right? Remember, gradient is change in y divided by change in x. I'll look at a very specific denominator, that is when the denominator is 1, the change in x is 1. What happens to our formula? It will be as such. Can you see change in x is 1? I will get this formula. And hence, this is how I explain the meaning of gradient. Gradient is the change in y when the change in x is by 1 unit. That's all it is, right? Gradient is the change in y when the change in x is by 1 unit. But I can improve on these two words. Y-axis always increases, so I don't need to say the word change. I can be very specific. I can say increases. This always moves from the left to the right. X-axis increases, whereas y-axis can increase or can decrease depending on my line. If the line is going upward, I have a positive gradient, then it means y values are increasing. If I have a slope going downward, I don't know if we have one here, maybe not, we don't have one, but if we have a slope going downward, then we have, I'm sure we have one somewhere. Nope, okay, never mind. If we have a slope going downward, then we say that x is increased. There you go. So here, oh, that's a shame we don't have the graph here. There you go. Right, so if we have a straight line going downwards, here I would say x is increasing, obviously, but y decreases. So I will be very specific instead of using kind of very uh, wide meaning of these words. I can be very specific here. So when the line goes upward, my y-axis is increasing and my x-axis always increases by 1 unit. Why 1 unit? Because it's there. When the line goes downward, my y-axis will decrease while my x-axis increases. So that's normal, that's perfectly alright. Right, so that was something on page 12 which I forgot to explain. So briefly guys, if I were to interpret gradient here, the interpretation of 2.6, so let me just summarize it here. Gradient is 2.6, right? I don't want to waste time with decimal places. So if I have to explain the meaning of this number, I would say that this is an increase in sales per thousands of pounds. I think, I don't know, I mean, you can check the units yourself. It's an increase. Why increase? Because the line is going upward. Can you see the gradient being positive? So it's an increase in sales, in thousands of sales. I don't know, you check. When the years of experience increases by 1 unit. So this is how much sales I expect someone to make, an increase in the sales, sorry, that I expect someone to make. Let's say increase in thousands of pounds. You have to double check the units. This is what I expect from someone who is moving from one specific years of experience to the next one. So from 4 to 5, from 7 to 8, from 1 to 2, from 10 to 11. The increase in sales in thousands of pounds should be 2.6 thousands of pounds. That's the meaning of gradient. Good. Sorry about coming back to page 12. Let's go back to page to residual. So we've discussed residual. I think page 17. I can't remember where it was. Yeah, okay. So I think that's pretty much clear now. Residual. The last one I want to discuss, I was asked to discuss, is briefly. I've just noticed this. This is one example on population, and I can't remember where it is. Population and sales. So sales depends on population. That's my x-axis, that's my y-axis. There you go. So just ignore this for the time being. That's my population, that's my sale, and if I plot them, it is a little bit tedious for me to read, right? To read. And I also don't want to waste too much time on this because it seems not really an appropriate example. Because if I sorry, by the way, this is y estimate. How do I get this? By using this gradient and substitute the y, the x, sorry, here, and I would get the y estimate, and I can find the error by finding true value minus estimated value. If I decide to plot the errors, you can see it's not scattered all over the place. It's focused here, right? So this is not really a good example. This is not an example where I would waste my time to do forecasting because of some limitations. But what are we going to do? We can't just say that the example is wrong. We have to see mathematically how we can improve on this. These are the graph I've shown you, but this is from SPSS. Now briefly, this is what is being discussed here as data transformation. It means let's transform all this. We can't work with this for obvious reasons I've just discussed. So I'm not saying manipulate the data. It's not manipulated. Actually, it's transformed into something which at least makes some sense. So one way to transform is usually to use log. So for example, instead of, oh come on, I have to keep moving up now. So instead of right, never mind. So instead of this one, instead of this equation where y is sales and x is population, number of people, instead of this I will apply logarithm to both sides, right? Now, that's where the mathematics might get slightly tedious for some of you. I hope not, but um, I don't know how to do this here. Um, Let me try quickly. So anyway, before I do this, before I show you, so instead of to avoid these limitations and discrepancies, all these craziness, what we can do is instead of x and y, we do log x and log y, log to base 10 or ln log to base e as well. It could be fine. So instead of doing this or focusing on this set of values, I can focus on these set of values by applying log. So if you check this formula here, log base 10 of this number, give me this one log base 10 of this number, so and so on. So I don't want to focus here for obvious reason. I want to do this one instead, right? So that's my new x and new y. I can then plot the graph. Can you see it's nice compared to the previous one? I have an equation here, and I can get the estimated value by using the equation, as you can see, and I get the estimated value, and I can find the error, which means the log y minus estimated y and gives you the error. And if I plot these set of errors which I've done here, I get the errors scattered all over the place, which is what I want. So basically that's what data transformation means. I hope this is clear. The only thing that I want to discuss is this. So instead of sales, I'll use log sales. Instead of population, I'll use log population, hence getting the formula here, as you can see. So these are the same values. Oops, these are the same values. Now what comes next is, remember, log x and log y have been used to help us. The true values were x and y, which didn't work because there were some limitations. But at the end of the day, I have to go back to my x and to my y. So I don't know how your log knowledge of log is, if you remember how to use logarithm. So basically, if I decide to remove the logs from this equation, if I decide to make sales subject of formula, get rid of the log and make sales subject of formula, I should get something like this. So I don't know, maybe you should practice a bit, try this. If you can't understand, then please get back to me on this. So if you don't know how to move from here, page 19, to here, page 21, let me know. So this is the only mathematics you need to play with. Otherwise, I think I've explained the meaning of data transformation, where you can use logarithms, whether it's base 10 or base e, to get a new graph which is fit for purpose. Right, thank you very much for listening. Remember, any question you can ask me, especially I will be expecting questions on this if you're struggling, but have a go, try it and see what happens. Thank you very much.